Welcome to Chapter 8. I'll pull up my screen so we can share. Chapter 8 is on time and geology. When we are dealing with geologic time, we do it two different ways. You can talk about absolute time and you can talk about relative time. We will start discussing relative time. So with relative time, a geologist is more concerned about the order of events than he is with the absolute time frame that they occurred in. We want to know, was the basalt in place and then the river cut through it, or was the river there and the basalt was deposited around it? The order of the events can make a difference. And so to do that, we spend a lot of time looking at rock formations in order to look at, again, relative interactions. So this is a generalized geologic map for the state of North Carolina. And you can see it's divided into different regions where there's the coastal plain, there's the Raleigh Belt, the Carolina Slate Belt, and so on as we go along. Here's the town of Statesville, there's Greensboro, there's Raleigh, Wilmington's down here, just to give you some sense of everything. Let's see, this is Interstate 40, and so, and here's Charlotte, so here's I-77. We're somewhere in this general region. I'm sorry I don't have a little better handle on it. So each color represents a different type of rock formation. And typically the rock formations are deposited in different time frames. So let's look at one that's a little more detailed than that. This is another generalized geologic map for the state of North Carolina, but you can see it has much more detail in it. And in fact, I think, yes, right here, this blue triangle is Catawba County. And we're somewhere up and through here in this blue region, if I remember. So Catawba County, because we're when you cross to go over the river into Caldwell County, you dip into a little bit of Burke County along the way. And Statesville is up here in Iredell County. So anyhow, now that you know where Hickory is, somewhere in this generalized blue region, each of the colors you can see by the legend corresponds to a different type of rock and also to a different time frame. And this one just gives us more details. So what is a formation? I've talked about them, but we really do need a definition. Formations are bodies of rock of considerable thickness with recognizable characteristics that distinguish them from adjacent rock units. So when you look at it, all the rock ought to be the same type and the same age, and it ought to look different from the things surrounding it. Formations are usually given names based on the types of rock that they're made out of and a nearby geographic place. So to give you an example, one of my most favorite formations is the Cranberry Gneiss Formation. That's gneiss spelled G-N-E-I-S-S. Remember that gneiss is a type of metamorphic rock. So it's near the town, it's a band of pink gneiss, and it's found near the town of Cranberry, North Carolina. And here's just a photograph of it with a penny for perspective. So to determine the relative age, we use three principles: the principle of original horizontality, the principle of superposition, and the principle of cross-cutting relationships. So these are all really common sense principles, but I'm going to explain them nonetheless. So the principle of original horizontality tells you that if you have layers deposited underwater, they're going to be horizontal. Well, that makes sense. In order for sediment to fall out of the water has to be calm. There would be nothing there to disturb it and keep it agitated. And so the heavy stuff would go down first, and then the next layer would come on top of that, and it would just keep falling down. Why underwater? Well, if it were just on land, I might drive through it with my car. A lizard might run across it. The wind might blow it. It might rain and wash it all away. Layers are not usually preserved well at ground level for very long. The environment just dissipates it. So the principle of superposition says that younger layers go on top of older ones. Well, again, that's common sense. The first layer that's deposited is the oldest, and the layer that comes on top of that is a little younger, and then on top of that is even younger, and so on. And then finally, the principle of cross-cutting relationships tells you that the disruption in a pattern is always younger than the pattern it cuts through. What does that mean? That means if you have a dike, remember that dikes are igneous intrusions. They were cross-cutting to the country rock they entered into. The country rock has to be there, and then the dike enters it. It can't go the other way around. So the country rock is in place, and then the dike comes in. The country rock is in place, and then the sill comes in. The country rock is in place, and then the rock gets tilted or broken or some other event takes place. I want to talk about correlation. Correlation is how we match things up. So there are different ways a geologist will look at rock formations and try to correlate them or match them, try to come up with some sense as to what series of events made this happen. Probably the most famous are the fact that there are rocks in South America that are a similar age of rocks in Africa, and that actually supports the theory of plate tectonics and tectonic drift, that South America and Africa were at one time together, and that it's only been over time that they have drifted apart and relocated. And we know this from the rocks that we find and also from the magnetic field in the rocks in the given area. And we'll talk more about that at a later date. So physical continuity. We look for a continuity in layers. Probably the easiest way to see this is if you think of something like the Grand Canyon. The Grand Canyon has a north rim and a south rim, and the Colorado River cuts right through it. So the rocks on the north rim match up with the rocks on the south rim. That implies that the rocks were in place and then the river cut down through the rocks. So that is using physical continuity. We can see the two cliffs, we can see the river, we can match up the layers. There are some distinctive bands of rock that run through the Grand Canyon that make this pretty easy to do. You can also use similarity of rock types. I talked about how South America and Africa have rock types that match up, that make us believe that the theory of tectonic drift is a very reasonable theory. Here, if you look at North America and Europe, and you look at, this is Greenland, Africa, and South America, geologists have matched up rock types in these different locations that lead us to believe that instead of their current locations at one time, these rocks were probably closer to this configuration. And it's all because we've been able to find fairly unique rock types in very different areas. And it can only be explained if the land masses actually shifted. And then we can use correlation by fossils. So if you have a group of fossils in a rock, it's called a fossil assemblage. If I had a rock and it had a fern imprint in it, and the little footprints of a lizard, or maybe it's an imprint of its skull, and maybe a seashell embedded. those three fossils would be my fossil assemblage for that particular rock. And so a geologist will use that fossil assemblage to try to come up with a date for the rock. And then if you find the same fossils in another rock, you can assume that they were formed at the similar time frame. If you get really lucky, you'll find an index fossil. An index fossil represents a species that didn't live for very long. And so what that does is it just narrows down our time frame. Some species live for millions of years, and some species are not suited to changes in their environment and they die out relatively quickly. So correlation by fossils is really important. Let's look at the graphic. So I have on the right side of my screen, I have layer 1 and 2 and 3 and 4 and 5 and 6. On the left-hand side, you can see that the fossil in this rock and the fossil in this rock are identical. That means they share a time, an age, that in layer number 4 on the left-hand side matches up with this fossil. So even though my rocks are different, because the fossils are the same, I'm assuming that they're the same age, that they formed in the same time frame. Then above on the left side, number 4, I come to this fossil. It doesn't match with number 5, it matches with number 6. That tells me that something happened between my layer 4 on the left and layer 6. It must mean that there probably was a layer 5, but it got taken away. Maybe there was an ice age and a glacier just stripped off all that rock. Or maybe I came in with my bulldozer and just carted it all away. Who knows? And then we see that we have rocks on the left that are not represented on the right. 7 and 8 are younger than the youngest rock on the right-hand side. Just like on the right-hand side, 1 and 2 are older than anything I've got on the left side. You'll notice where we have the missing rock, we have a wavy line. That wavy line is called an unconformity, and we'll come back to that. But it represents missing rock. In this instance, our missing layer number 5. It tells me there used to be rock there, but there's not anymore. Something happened. So let's see if we can look at 3 different fossils in a given rock and figure out the age of the rock. I have fossil A, fossil B, fossil C. Fossil A, this little dash line hits the mid-mark between 0 and 1. So fossil A lived between 1/2 and 4 million years ago. That's the time frame. Fossil A was between 1/2 and 4 million years ago. Fossil B was between 2 and 5 million years ago. And fossil C was between 3 and 6 million years ago. What we need to do is find the time where all 3 were alive at the same time. If we look at the diagram, were they all 3 alive 6 million years ago? No. A and B were not. Were they all 3 alive 5 million years ago? Well, no. B was alive and C was alive, but A wasn't here yet. At 4 million years ago, were they all 3 alive? Yes. A was just barely here, and B and C were well established. So we know that at 4 million years ago, all 3 could have been around. 4 million years ago, all 3 would have been around. All right? Let's go the other direction. So at 1/2 million years ago, were they all 3 here? Nope, only A. At 2 million years ago, were they all 3 here? No, B had just at the end of B's range, and A was well established. So it was A and B, but no C yet. I come down to 3 million years ago, and yes, C was here, B was here, and A was here. So you can see that all three fossils were alive from 3 million years ago to 4 million years ago. That's the only time when A and B and C, all three coexisted right in this little range. So I looked at my arrows, I came down, down, down to the lowest up pointing arrow. That gave me the 3 million years ago. And I went up, up, up to the down arrow that was closest to the top, and that was my 4 million years ago. Sorry, I had struggled to give it a name. So in the 3 to 4 million range, that's the age of the rock that contains all three of these fossils. So there's another way to do this. We'll go ahead and write it all out so you can see my logic. So I did it on the graphic, but we could have written it down. We could have said fossil A, okay, 0.5 to 4 million years ago. Fossil B, 2 to 5 million years ago. Fossil C, 3 to 6 million years ago. So if we look at our little numbers, our starting numbers, we picked the biggest one of those, that was the 3. We look at our ending numbers, our 4, our 5, our 6. We pick the smallest one of those. The smallest one of those is number 4. And so 3 to 4 million years ago is the range that we have, 3 to 4 million years ago. So our standard geologic time, we'll move on to that. So standard geologic time is based on fossil assemblages. Those are the fossils that coexisted at that time frame. We divide our time up into 3 eras: Cenozoic, Mesozoic, and Paleozoic. Cenozoic is new life, Mesozoic is middle life, Paleozoic is old life. We are in the Cenozoic era, and each era is then subdivided into periods. I should have highlighted that. Eras are divided into periods, and then periods may be divided into epochs. Not all periods are divided into epochs. So we look at the time before fossils were easily visible, and we call that Precambrian time. We used to say that there were no Precambrian fossils, and now we know better. We have better magnification, and we now understand that the vast majority of Precambrian fossils are microscopic. They're there, but they're very, very tiny. They're there, but they're very, very tiny. So let's look at our little graphic. We have the Cenozoic era, the Mesozoic era, and the Paleozoic era. And you'll notice they've got some cute little things over here to tell you what you might have found alive during that time. You'll notice that this is the Jurassic period and the Triassic period, the Cretaceous. So see up here, we're in the Holocene period. And then here's another graphic that maybe isn't as colorful, but has a little more information. So it has eons, which we didn't talk about, then our eras, then the periods, and the subdivision to the period, remember I said was the epoch. And then we have our time frames. And again, what would you have expected to have seen then? One thing you'll need to notice that the dinosaurs are way down here, and humans would be way up here. So not at all in the same time frame. All right, we want to look at unconformities. These will help us with our lab. So an unconformity is a surface that represents a gap in the geologic record. I have talked about it when I mentioned the little wiggly line and the missing rock layer in a previous example. So with an unconformity, the rock unit immediately above your contact is much younger than the one below it. And that makes you wonder, what happened? Where did the rock go? Why do I have this gap in my ages? Well, most unconformities are buried erosional surfaces. So maybe a glacier came in and dragged away that layer of rock. Maybe I came in with my bulldozer and dragged away that rock. A lot of things could have happened. Maybe there was a lot of flooding going on and things were carted away because of that. So this erosional surface, the erosion takes place at the surface, but then it gets covered up. And that place where the change takes place is called the unconformity. They always occur at surface level, and we have three distinct types. The first is a disconformity. A disconformity is just a place where a layer has, or more, has disappeared. So if we start out with three rock layers, 1, 2, and 3, and I come in with my bulldozer and I take away all of number 3 and half of number 2, it looks like this. Notice the wavy line. And then I change my mind and nature brings in a new top layer and it goes 1 and 2 and 4. And again, remember the numbers give us the relative ages. 1 is old, 2 is a little younger, 4 is a lot younger because we made 3 disappear. So this line where the change takes place is our disconformity. Let's come down, and here's a photograph of it. You can see that this bottom part is a conglomerate, and on top of it, if you were able to look at it, you'd realize that it's limestone. And they're very different ages and indicate that there's a disconformity. I'll get my words out in a minute. A disconformity, a layer has disappeared. So if we come down, we have an angular unconformity as our second type. With this, you have either folded or tilted layers. And on top of that, you get new rock. So we have layer 1, 2, and 3. They get deposited, and then maybe I compress them in, and it gives us that little wavy pattern we're seeing where the rock layers are folded. And then we even it off maybe a little bit or not, and then younger rock comes on top. So right here, where we change from being curvy to not, is our angular unconformity. And in our photograph, you can see, this is in the Grand Canyon, that these rocks angle down, but the ones on top come straight across. So we have an angular unconformity right here, an angular unconformity kind of cutting across almost in the middle of the photograph. A non-conformity is an erosional surface on plutonic or metamorphic rock covered by younger sedimentary or volcanic rock. So plutonic rock is a kind of igneous rock that gets buried underground. So it would represent igneous intrusions at depth. And then metamorphic rock, again, we've said, takes place at depth. So these non-conformities, the base rocks get deposited at depth and they're not sedimentary, which is why in the drawing, they're usually indicated with little jagged lines. So 1, 2, and 3 little jagged lines. I come in with my glacier and eat away all of 3 and half of 2. That's the wavy line. And then we deposit sedimentary rock layer 4 and 5 on top of it, or it could have been volcanic rock. It could have been a plateau basalt that comes out and spreads over the area. That could happen. So that would be layers 4 and 5. Right here where the change takes place is our non-conformity, because below it is non-sedimentary rock. And again, here's a photograph of the change, and you'd have to know something about the rocks to even recognize that that's what we're looking at. Okay, let's consider a geologic cross-section. So this box represents the side of a mountain. We're expanding our road, we're cutting down through, we want to cut away some of that rock so that we can put in a wider road. And when we do, we notice all the different layers, and they're just really cool. So we're going to look at them. So we're up here standing on the top, We're up here on the top, and there's a guy down here at road level, and we're seeing all of this. And so we figure we want to know what's going on. But we know what these kinds of rocks are. We know that this one is sandstone. Here's my little symbol for it. That the one below that is marble. That this one represents conglomerate. That the little dashy lines go to slate. And that the dark shaded rock is basalt. It looks suspiciously like an igneous intrusion, doesn't it? This looks like a dike coming up and cutting across, and this little side piece is a sill coming out from it. But I'm not going to worry with that right now. So we want to do step number 1, list the rocks vertically in order of deposition, oldest on the bottom, youngest on the top. So the easiest way is to start at the top and work your way down. So the rock at the very tippy top is sandstone. So on my step 1, that's what I'm going to write down is sandstone. And then directly below sandstone, we come to this unshaded, and that is marble. And so directly below that, on the line below it, I'm going to write down marble. So we have the sandstone and then the marble. Directly below that is our conglomerate. So that's what I'll write down, conglomerate. We're almost done. And so we had sandstone and then marble and conglomerate. We said we would ignore the igneous intrusion right now because that's not really a rock layer. And now we have this. The slate is our last rock layer. It is on the bottom. So we have our 1, 2, 3, 4 rocks, sandstone, marble, conglomerate, and slate. Oldest is on the bottom, youngest is on the top, which is why when you're doing your layers, you want to start at the top and work your way down. It's much easier. All right, the second step says to list the changes. We want to list the changes. So what I want to know is what took place where. Well, we do have this igneous intrusion. Here is the dike and here is the sill. Because the dike and the sill are connected to each other, we ignore the sill and only look at the dike because the dike goes up higher. It cuts through the youngest rock compared to where the sill goes. So the dike and sill cut through the slate, the dike and sill cut through the conglomerate. The sill finds a little side path at the conglomerate and it's happy on its little journey, but the dike keeps pushing through, it hits the marble and then it stops. It does not enter the sandstone. So we know that between sandstone and marble, that's where our dike and sill combination are, between sandstone and marble. So I'm going to put in a little arrow right here between sandstone and marble. And I am going to, hopefully, oh, that's not what I wanted to do. Let's see if I can make it work. So between sandstone and marble, and that is our dike and sill. So I'm going to type in dike and sill, dike and sill. My little arrow should have gone with that. It isn't pointed very well. I might have to tilt it some. So the dike and sill go right there. Okay. So we've got that taken care of. You could have called it the basalt dike and sill if you had wanted to. What else have we got going on? Well, let's look at the slate. The slate is not horizontal. You can see that the lines don't go across. They got an angle. And the slate wouldn't have been deposited like that. We said, well, we have to assume that the layers start out horizontal and then they're tilted. So the slate would have been deposited and now it's tilted. Does the conglomerate look tilted? No, because if we look at its top layer, it goes straight across. If the conglomerate and slate had both been tilted at the same time, the conglomerate's top layer would have matched the slates and it would have come down in an angle also. So we know that the slate got deposited and then it got tilted and then the conglomerate. So between slate and conglomerate, there is another thing to insert. And that would be our tilt. I'll draw a little line out and I'm going to say tilt. All right, so we have the dike and the sill. We have the tilt. We've got one more thing, and that's this wavy line right here between the sandstone and the marble. The wavy line is an unconformity, and it comes between the sandstone and the marble. But I've already got a line there. That's where my dike and sill is. I have to decide, does my unconformity come above the dike and sill to make it younger or below the dike and sill to make it older? When you have an unconformity, you need to assume that it is in the same place as a second event. You need to assume that the unconformity is probably the younger event, because unconformities happen at surface level, and things like dikes and sills happen below that. So we probably want to assume that my unconformity happened above. So I'm going to draw in a line, and that will be for my unconformity. So I have my unconformity, my dike and my sill, my tilt, which the computer tells me I should have capitalized. It doesn't like that I didn't capitalize it. Okay. So we have sandstone, unconformity, dike and sill, marble, conglomerate, tilt, and then slate. All of what we just did is step 2, insert the changes. All of what we did is step 2, insert the changes. And now we want to list the rocks and the changes as a geologic column. We're going to let one be the oldest. That means it'll be slate at the bottom. And whatever our biggest number is will be the youngest. So we're going to write down slate, and then the tilt, conglomerate, marble, dike and sill, unconformity, and sandstone. Or if you want to go the other way around, you can say we'll start with sandstone at the top, unconformity, dike and sill, marble, conglomerate, tilt, and slate. And that is our step 3. And that's what we did. You should be able to match up this with our final configuration down here. The missing thing under the blue box is where I actually showed this. I wasn't sure if I was going to draw it for you in real time or not. And so we have the 1 is the oldest rock, and the biggest number represents the youngest rock. Think of it as children in a family. Child number 1 is the oldest. If there are 6 kids in your family, number 6 is the baby. So absolute age, radioactivity really helps us determine the absolute age of a lot of different things, and rocks are no exception to that. Right now, we think the Earth's in the neighborhood of 4.5 billion years old, but that is certainly subject to change as we learn new information every day. So how does radioactivity do this? Well, there are some things that are just naturally radioactive. They have too much energy and makes them unstable, and in order to achieve stability, they give off some of that energy in the form of radiation. Typically, you would have a radioactive element give off either alpha particles or beta particles or gamma rays. So alphas, betas, and gammas. The changes, when it does this, it takes away mass as well as energy. And it does this until you get a stable end result. So as an example, if I had uranium, that's what the U stands for, 236, that's the isotope, uranium-236, and it gave off an alpha particle. That's what this funny little symbol is, a lowercase alpha. it would turn into thorium-232. So TH is the abbreviation for thorium. So uranium-236 is the parent. This is the radiation, the Greek letter, the little alpha, and the thorium-232 is the daughter. So it's always parent by itself, radiation and daughter on the opposite side of the arrow. So the time required for half of your radioactive sample to decay or change into your daughter isotope is called the half-life. Called the half-life. And I think the easiest thing, that means if you start out with 100 grams of radioactive substance and its half-life is a minute, after a minute, you don't have 100 grams of that starting isotope, you only have 50. And the other 50 have turned into something else. Maybe all into the daughter, maybe into the daughter and something else. So let's look at this. So how do we figure this out? We'll do an example. Suppose we have potassium-40, has a half-life of 1.3 billion years. If you start out with 20 grams, after 3.9 billion years, how much do you have left? Well, first of all, we need to know the number of half-lives. To do that, you take your total time and divide it by the time for one half-life. Total time divided by the time for one half-life. So our total time was 3.9 billion years. One half-life was 1.3 billion years. So 3.9 divided by 1.3 gives me 3 half-lives. That means that I need to take and represent the decay 3 times. So we're going to start out with 20 grams and divide it by 2 to find out what would be left at the end of the first half-life. So 20 grams divided by 2 gives me 10 grams. That's what you have left at the end of the first half-life. 20 grams divided by 2 gives you 10 grams, and that's what you have left at the end of the first half-life. So for the second half-life, we don't start with the 20, we start with the 10 because that's how much radioactive substance we have. So we take our 10 grams, divide it by 2, and get 5 grams. That's what you have left at the end of the second half-life. 10 grams divided by 2 gives you 5 grams, and that's what's left at the end of the second half-life. We are almost there. One more half-life to go. So take our 5 grams, divide it by 2, and we have 2.5 grams. So you'll have 2.5 grams at the end of the third half-life. What happens to the other 17.5 grams? Well, it's turned into other isotopes. That's what radioactive decay will do. It gives off energy and it turns into other isotopes. You ought to be able to do an example like this for a quiz, and you'll have some practice problems with it for homework. Radioactive dating. So to determine the age of a rock, you measure the amount of radioactive isotope present, the amount of daughter isotope present, and if you know the half-lives, you can figure out the age of the rock. Now the example we used only did whole numbers of half-lives. In reality, you can have fractions of a half-life, but that requires a more complicated approach, and we won't do that for us. That equation is much more complicated. So we can do absolute ages using half-lives. Some examples of isotopes that are used. Carbon-14 is used for organic material. So if you found a piece of cloth and wanted to know how old it is, you'd use carbon-14. If you found a piece of paper and wanted to know how old, you'd use carbon-14. If you found a cooking pot and it had food residue in it, you could use carbon-14. If you have a rock, carbon-14 is not especially useful. You'll notice that the carbon-14 turns into nitrogen-14. Also that carbon-14's half-life is a little less than 6,000 years. That means its useful range is only for about 100 to 30,000 years. So anything older than that, you're going to have a hard time using carbon-14 to tell an age, even if it is an organic compound. Potassium-40 is used quite a bit. It turns into argon-40. Its half-life is 1.3 billion years, and it's a very useful isotope. Rubidium-87 is useful, as well as two of the isotopes of uranium, uranium-238 and uranium-235. So if we take what we know about relative ages and absolute ages, it really helps us narrow things down to get a good understanding of orders of events and ages at which they took place in. I think we'll stop there. Stop our recording.